Okay, so this is pretty straightforward, especially for the match model. There's only one variable that's being summed over, so there really isn't any factoring that matters in terms of computational complexity. You know, every single one of our terms has kappa in it, and we're summing over kappa. So clearly none of those things can be factored outside of that summation. No need for any parentheses. For the mismatch model, the problem is a little bit more interesting. We've got two variables, kappa and lambda, that we're summing over. And if we look at our joint probability equation, we've got two terms that have kappa but don't have lambda, and we've got two factors that have lambda but not kappa. So the clear possibility here is to be able to, for example, factor the terms that have lambda but not kappa outside of the summation for kappa, and conversely, we can factor the terms that have kappa but not lambda outside of the summation over lambda. So what we end up with is actually two separate computations that can be done completely separate from each other, and then just multiply those two numbers to get your total result. Any questions about that?
It's a little bit confusing the match model, where kappa is both like a conditioning variable and also a condition variable that doesn't have any effect.
Well, simplistically, you know, as far as the summation sign is concerned, you can sort of forget what each one of those individual factors are, right? You know, is it a probability? Is it just some function? All that matters is it a function of kappa, right? If it's not a function of kappa, you just factor it outside of the summation, right? And in this particular case, they've all got kappa in them. So we can't factor anything outside of the summation, so we're just stuck with our basic form. You didn't need to think about it any more than that. I'm not sure if I answered your question.
Yeah, I mean, I understood that part, the math part of it. I think from the knowledge, because you had talked about this yesterday, in terms of like summing over.
I see. Well, I mean, one way of thinking about this is that this whole expression represents a joint probability of x, s, and kappa given theta. Everything inside this summation, we could just rewrite that as probability of x, s, kappa given theta, right? So we're actually summing over something that is a subject variable, right? And that's totally legal. We just are eliminating it from the joint probability to get probability of x comma s given theta. But, you know, you're right that we should be thinking about what we're doing. You know, is it valid to do this summation or not? And it is. Other question?
Yesterday we learned that you know, when there's only one dependency, say on kappa, in the second example there's only one dependency, but on the first example there's two. But when there's only one, you said we could like bridge that gap and forget about the kappa and, you know, kind of like sum over it and then jump over it, remove the variable basically from the dependency graph.
Okay. So this is a really great question. You're way ahead of me. I will actually maybe jump a couple slides ahead to something that I was going to talk about, exactly this issue. No. Why not talk about it now? This is great. So here's the question, more or less, that you just asked, which is, you know, what happens? You can think of it as, well, you know, what happens to the information graph when we do this summation and we get rid of kappa? Concretely, you could ask, well, what graph structure would you draw for the information graph without kappa? And we do the summation to compute, for example, pxs theta under this model, and I think you'll agree, we can get this by summing over all possible values of kappa from here, right? All right, so what should the information graph structure look like? Well, how do we think about that question? What are the questions we have to ask ourselves to begin cracking that question? I mean, the bottom line is, what variables are going to be in the resulting information graph?
Excess and theta.
Yeah, so we're going to have 3 things instead of 4 things. So we could start by just putting those 3 things up on the board. I'll just erase this here. Actually, maybe this part is useful to record, so maybe I'll do it over here. I always dreamed of having my picture up on the big screen upside down. So I finally achieved my boyhood dream. So we could just draw our 3 variables. Somehow or another, these things are going to have arrows between them. Concretely, the possibilities are pretty constrained, right? I mean, we pretty much know, for example, we were probably going to draw some kind of edge going from theta to x and s. Are we going to draw any other edges? Well, there's not very many other edges to draw. I guess let's try to ask ourselves, well, what question is in play here for the one decision that we need to make about this picture? I mean, if we end up drawing, for example, arrows from theta to x and s, what question is left, and what issue is in play for that question?
What's the direction?
So you're focusing the issue on the question of possible edges between x and s, definitely. So absolutely. That really is the core question here, because we can say, well, based upon what we've been doing already, clearly there should be some kind of dependence on theta, and we can start by drawing in those edges, and then we're left with this question down here, which, when you think about it, is exactly the question that you just asked. Because if x and s are conditionally independent given theta, then what do we do here? Sorry? Well, in information graph picture terms, there's a decision about what to do down here, right? And if we say that x and s are conditionally independent given theta, then what do we do down here? Nothing. Exactly right. So this picture, as it stands, is an assertion that x and s are conditionally independent given theta. They're connected. They're not independent. but they're only connected by theta. So conditionally independent given theta. Whereas if they're not conditionally independent given theta, then what's the information graph? Yeah, we gotta put some kind of arrow connecting these. And the question that you asked, a really great question, is which direction? And I guess for the purposes of this discussion, I would say it's basically arbitrary. I mean, unless there was some like good experimental reason why we should consider, one piece of data to be more primary than the other, I would say it's arbitrary which direction you're going to draw this in. I would also mention that here, the lack of conditional independence, if that were the case, would basically force us to draw an edge down here, even if that doesn't, make sense causally. In other words, that this is an actual physical model that says somehow or another information goes from the fact that the machine read, 0.7 here to somehow or another that some other machine is going to have to read 0.2 or whatever it is. And when you confront situations like that where your information graph is forcing you to put in edges that you don't think are physically plausible. In other words, it's implying a causality that you think doesn't represent reality. That's a suggestion you're missing hidden variables in your information graph. In other words, there's something going on inside there that's the actual causal explanation of your data, which is not represented by your information graph picture. Okay? So now, coming down to the question of this specific model, when we sum over all possible values of kappa, what should we actually do down here? To be or not to be? We need an edge down here. And, as I said, the directionality is kind of arbitrary, so, I guess conceivably you could put an undirected edge just to say, well, the directionality is arbitrary. But we would definitely need to draw an edge down here. If we're restricting ourselves to undirected edges, we could just, toss in something like that. So what is this? That's just the full general chain rule, right? And we've got 3 variables and we've got 3 edges. And so by eliminating kappa from the picture, we're basically forced to a picture that looks like the full, just standard general chain rule for 3 variables. Questions about that? Okay, so let's go over here. Let's say I've got some polymorphisms like 10% allele frequency or something like that. And then I have observations down here, and let's say for x, I measure a value of something like 0.5, which implies that that person had one copy of the polymorphic number. So now the question is, does that predict anything for what we'll see for S? Or is S simply its likelihood is the same as what we would get from our original value of theta, not taking into account what we observed for X? So, what people know. Yeah, I mean, under this model, under this specific model, so I can use simple. Yeah, I mean, if over here we see a clear signal that the person's got polymorphism. Under the match model, we can see exactly the same thing. Because the match model says it's from the same person. Right? So X and S are not conditionally dependent given theta. If you see an X value of 0, it's going to tell you should see something like 0 over S. If you actually see 0.5 for X, it's telling you should see something like 0.5 for X. Just subject to the detector noise, right? There's detector noise for the reading of kappa by X and S. Other questions?